One of the things I do, I'm an advisor to Sightline Climate, that's a research and analytics organization focused on energy and climate-related investments. And they've given me permission to use some of their slides, so I'm going to show you some of the analysis that's come out of that. First of all, if you look at the pattern of data centers, they've tracked some well over 700 data centers around the world, above 50 megawatts capacity in terms of announcements. And what you can see from here is there's a lot of announcements in terms of plan to build data center capacity in terms of gigawatts. But we are seeing some signs of delays, not that many cancellation, but certainly delays at the moment. So whilst there'll be announcements in the future, don't necessarily assume that all of this is going to translate into reality. For example, in 2025, actually achieved was 5.8 gigawatts, which is still a lot, but the red area are delays, which will probably happen in later years. And the same is true for some of the other areas. We're seeing the amount of construction that's going on, for example, in 2026 is only a small proportion of the expectation. If you look around the world, particularly in the US, it's very concentrated. So Texas has more capacity coming online than all other states, and for that matter, many other countries. And we are seeing a few signs of delays at the moment. This is one example in Silicon Valley, delayed for over 6 years due to lack of grid capacity, and in particular transformer capacity has been a constraint. So that leads to delays. It may transfer into other areas, into other regions that have more grid capacity, but it's a slight warning signal, if you like. Now, I focused on the problems. What about the solutions? So one of them is to get firm capacity. And this is just some of the examples of the hyperscalers. I'm not going to go through these in detail. Many of these examples are nuclear. Some of it's nuclear capacity that exists today, some of it's new nuclear capacity, particularly small modular reactors that are planned to be built. So that's one way of getting firm power. Fervo, by the way, isn't nuclear, that's geothermal power, which is very good for providing firm power. And it's not just firm power. There are other technologies that can deliver the flexibility that grid operators now need. So workload orchestration, for example, Emerald AI and Hammerhead are just two of the examples. They're essentially orchestrating to try and balance the needs of the data center for compute with what's available on the grid, and to provide that flexibility or optimization to try and keep the GPUs running, but equally to try and balance the system. Cooling and operations, again, some of these examples are somewhat similar, and it's about balancing when you need actual cooling to fire up. Can you delay it for a period of time? Does it really matter if that's when the grid is particularly constrained? So it's another way, if you like, of optimizing and balancing the system. And then there's Nostromo is a completely different example. They have, I think it's called an ice brick, essentially something that can store cooling and then be used when necessary. Generation and storage, Enchanted Rock, they're, for example, providing gas, but almost on demand. You can ship in gas generators, use them partly as a bridge to when the grid may become available to a data center, but also to provide the reserve capacity that is currently done by diesel. Conduits building out renewables and storage, so that's another way of providing that flexibility and balance. And then virtual power plants, I'm sure, are very familiar to this audience. So those are some of the examples in terms of the energy part of it. But what about the semiconductor players? Because we hear more and more demand for compute, but what are they doing to address this? Well, the fact is they're very, very focused on computational efficiency being matched by energy efficiency. So in other words, it's not just about how many tokens per watt you can produce, it's how many tokens per megawatt can you produce? And the reason they're so focused is they realize that energy is otherwise going to be a gating factor for AI and for all the services and chips and so on that they can provide. So this is just one example from NVIDIA's GTC. It's its recent conference. You can see the man in the leather jacket down there. He needs no introduction. And in terms of the way to read this is the horizontal axis is a measure of computational intensity to get a token. Tokens are essentially words. So if you're asking a query, for example, if it's very computationally intense and you're going round and round in the loops and chains of thought, you'll be over to the right and it may actually be quite an expensive query. On the left, there's less computational capacity needed to answer that question. So that's just one measure, if you like, of complexity. The vertical axis is how many tokens you get per megawatt. These curves all slope down because obviously as the problem becomes harder to solve, you're going to use more energy, you're going to use more compute. So you'd expect these to go down. What's really striking, though, is that on the energy efficiency measure, where the higher the better, you can see how much progress has been made. 35x from one generation of technology to another, and another 2x for a medium complexity calculation. And also, NVIDIA, with its extension to Grok, the technology, that's Grok with a Q, the technology that it licensed, it's able to extend that improvement in energy efficiency right up to the premium level, so even for more complex calculations. So the message I really wanted to leave you with is that this is a semiconductor challenge as much as it's an AI challenge. And that's it. Thank you very much.